So welcome back, everyone, after a 2 weeks break due to the very exhausting conference, at least for me. Very happy to have today Aurélien Drezet, who already gave a talk last year, I think. Good. We are keeping track of your research, that's good. And thank you again for coming, for giving this paper. I'm going to say welcome to a couple of new people that never came. Thank you for that. You are very welcome to join whenever you want. So yeah, next week we're going to have Hippolyte Jourdain, which might share a paper weekend. We don't know. I'll let you know if he does. But again, you're all welcome. Nice. Okay, so Aurélien Drezet from Institut Néel is a CNRS researcher who's going to speak about Lorentz invariant, retrocausal, and deterministic hidden variable.
So thank you very much, Christian. Thank you for letting me speaking about the Bohmian mechanic once more. So it's discussed already 2 times during this seminar. It was about the probability. And today I will discuss about some other issues which are much more, I would say, speculative about the relation between hidden variable, deterministic hidden variable, and relativity, special relativity. And I will try to emphasize some points that I think are interesting and could be useful for developing maybe a future Bohmian mechanic. Which will be more in agreement with relativity. So the first thing that I would like to say is a few words about the standard Bohmian mechanic. So how it works, yes. So the first thing to say is that Bohmian mechanic can be understood in a simple, physical and intuitive way. If you imagine this kind of picture where you have a particle, which is a kind of surfer, which is moving on top of a wave, and the wave is moving around an obstacle like an island, and so the particle is following a specific path, but it's a completely deterministic motion, and at the same time you can have an interference effect between the different waves. So this illustrates quite well, I think, the motivation, the original motivation for the Broglie-Bohm pilot wave theory. And you see the contrast with this picture, between this picture and the Copenhagen way of thinking is very strong, because in the Copenhagen way, we refuse to say where is the particle going, so we don't have trajectories anymore. So this is, of course, only a picture, an illustration. The thing is, if we try to go to the dynamic more precisely, it's not so very difficult. You can see already from the non-relativistic model, the Broglie-Bohm dynamics already obtained in the 20s. So 1920s, 1927, 1926, you have this wave function, a solution of a simple Schrödinger equation, and you can write it as a complex number, and the definition of the dynamic is given by the velocity law, the guidance law, which is the gradient, the velocity is the gradient of the phase. And this is very similar to the old mechanic Hamilton-Jacobi equation in classical physics. But the thing is that if you go now to the second order law, if you watch the Bohm-Newton version of the dynamic, you have something which is a bit different, because you see then the force acting on the particles, the mass times the acceleration, is divided into 2 terms. The first one is the classical force, which is a Newtonian force, let's say, and then the second one is the quantum force. I will not express in detail here, but it's a quantum potential, which is which is acting on the particle. And this kind of quantum potential suggests an external agent, an external system which is acting on the particle. So this will be a part of the discussion after about the ontology of the wave function. But let's say already that what is interesting is that you're not only dynamic, but also statistics. So you can recover Bohm rules, assuming some postulates, and which can be debated, because there's a lot of things to say about that, but I will not do it today because I did it already 2 times before. So the thing is that most important properties for Bohmian mechanics is probably its very strong contextuality, which depends also on non-locality and different things like that. So it affects the notion of measurements, of quantum measurement that you have in literature. For example, if you take the double slit experiment in standard textbook, you know that if you want to observe fringe, then it's fine, but then you cannot observe the hole from which the particle is coming from. But in Bohmian mechanics, it's a bit different. You see that, of course, if you put a quantum system, which is a Witch path detector, which is able to detect where is the particle coming from, so you will erase fringes, the trajectory or something like that. But in Bohmian mechanics, what is nice is that if you take, for example, this system here, you have the base lane, the medium lane here, the particle cannot cross this lane. So if you detect the particle in the upper space here, you know for sure that they were coming from A. So you have already an information between path and interference in Bohmian dynamics. So it means that in Bohmian mechanics, measurement must be interpreted afterwards, so not before. So that means that you must already have the notion of the dynamic before to understand measurement. Otherwise, you have some classical prejudice which make you, it leads to very wrong conclusions, like surrealistic path or things like that. Anyway, the point is that the wave function is also a strong subject of discussion and debate. We saw that during the last seminars by a couple of people like Vera, Matarez, Bagheera-Lori, Jean Brickmore also discussed about that, Peter Lewis and Tim Modin. They all discussed about the problem of the wave function, the status of the wave function in Bohmian mechanics. So I think there is at least two ways of watching that. The first is to say that the wave function is probably a physical agent. So as I mentioned before, from the picture that with the surfer. So the wave function is a guiding field, so existing independently of the particle. So the primitive ontology in this kind of language would be both the wave function and the particle. And the motivation for that is maybe the quantum potential, which is suggesting an external field acting on the particle. There are also in modern way, in modern literature, different things which are suggesting that the wave function is the real stuff. So I can mention the weak measurement protocol, the protective measurements, and the interaction-free measurements, which are associated with the work of Leigh Weinman, for example. There also the PBR theorem, which is very interesting, but I will not discuss about it today. And all that somehow suggests some reality of the wave function, but at the same time, everything is indirect in the sense that the wave function is not really directly measured. What you measure is only at the time, always at the time, at the end of the experiment particle motion. So this is a thing to remember. But the second way of thinking about the wave function is nomological feature. It's very much discussed in the modern literature. So it would mean that the wave function is simply a law, a dynamic. So the primitive ontology in that picture will be the coordinate of the particle. So one motivation for that is the wave function in the configuration space so it's propagating in the high-dimensional space. So this is different from the three-dimensional space of the real world. So it would be very strange for the kind of dynamic with the wave function and the particle together, knowing that these two objects are not in the same space. But hopefully it could be debated, and it could be because we could imagine that everything is on the configuration space, like David Albert, for example. But this is very interesting anyway. There's no consensus on that. Another thing to say is that there is no back action apparently of the particle and the wave function. The wave function is guiding the particle, but not there's no collapse in the Bohmian mechanics. So it also suggests that that something strange is happening here. It's not necessary to have a picture between Psi and X together as dynamic entities, because we don't have the action-reaction between both systems. There's still some things which are not clear, because the law is strange here. The law is depending on generally time dependent. So, but the law, as we generally assume, is not necessarily evolving in time. But this is connected to this this idea of the quantum potential here, which is suggesting an external field. So you see the topic is not very well. I think it's metaphysical in many sense. Okay. So now today I'm going to speak about other things which are not very clearly understood, and probably could be debated. is the status of non-locality. So if you take the wave function, the Schrödinger equation for many particles, so you are in a configuration space, you have many positions, you have the guidance formula for all these particles, and you have the instantaneous connection between the particle, which is driven by the quantum potential. So you have a non-local system, and then the point is that you have an absolute time in this non-relativistic equation. So you have a Newtonian time, and the non-locality suggests an action at a distance, an instantaneous action at a distance. The thing is that this properties survive also for quantum fields and relativistic equations like the Tomonaga equation, for example, or the Dyson equation, and all the things like Dirac equations also containing this feature. And this is because you have always this time derivative here, with this first order time derivative, which is appearing in the Schrödinger equation, and you always have this kind of foliation of space-time, which is inducing this instantaneous connection. And of course, the most curious feature is the non-locality. So I will give you an illustration, which is very well known, but still very, very interesting. This is coming from an old paper by Rice in 1997. So imagine that you have two particles, positively charged and negatively charged, which are entangled in a perfectly entangled state like this one. So one is in the galaxy A, and the other one is the galaxy B. So the beams are like that. For example, the V plus beam is entangled with the V minus, and the A plus is with the A minus. So this is like that, and they can propagate freely and they can cross. And okay, this is nothing happening in standard way of thinking, but in Bohmian mechanics, we know that the path cannot cross. It's again connected to the same thing from the double slit experiment. So they cannot cross, so you have something like that, they are bouncing. Okay, this is looking a bit surrealistic, but it's hidden because you cannot see that directly in your experiments. It's hidden by the statistics. The no signaling theorem prohibit to use that for faster than light signaling. But the thing is interesting, because if you put a mirror here in between, if Alice in the galaxy A put this mirror, which is reflecting both sides, so the particle will go that way, but this will affect instantaneously the second particle. We know the Bohmian path will cross. And this is really curious because you have only an illustration of the non-locality and action at a distance. And okay, this is a well-known illustration, but you can imagine that it has consequence when you try to combine this with special relativity, because special relativity tell you that if you are outside of the light cone, then the order, the causality order is depending from the reference frame in which you're watching the problem. So if you think about instantaneous connection in order reference frame, it could be that A is before B or B before A. So it sounds like if you're using tachyonic signal, but the order of the causation is changing. And also, it's not very clear what is prohibiting this kind of causal loop. Imagine that you have two particles at point A, the particle is connected to the second particle at point B with this hypersurface here, this space-like hypersurface. And then there is another link here with the other point of the same particle here, and you have the possibility to have a causal loop, like the grandfather paradox. It means that you could kill your grandfather before you're born, and this would look like a really paradox. Okay, this would be a problem. So this has to be somehow avoided from the start, and so we have to clarify a bit this issue as well. So the aim of the topic is to discuss a bit more this different problem. I will discuss probably more this one because it's very connected to Bohmian mechanics, but I can come back to that after if you need. Let's see what is the relation between Bohmian mechanics and Lorentz invariance and causality. So I'm going to discuss a very nice theorem which has been derived by many people. I think the first one was Lucien Hardy. Then there's also a paper which is related by Conway and Cohen, and which is based on what is called the free will theorem. And then there's a nice paper by Nicolas Gisin as well, which is a bit later, but not so much, also connected to this topic. I will essentially discuss about the work of Hardy and even more about the role of Gisin here. the work of Gisin, even though I'm using the semantic of RD. The paper of Conway and Cohen is different because it's discussing the so-called Cohen-Specker property of contextuality, and the two other works are focusing on non-locality and better EPR, but anyway, it's related. So the RD is using a nice terminology, a nice semantics. I will use the same one. He's first introducing what is called the Lorentz invariance of hidden variable theory, LIFT. And I can read this. It's for a given run of an experiment, that is for a given set of hidden variable. A hidden variable theory must give the same predictions for outcome of measurements, regardless of the frame of reference F in which it is applied. This is quite intuitive definition of relativistic dynamic. But then he's trying to introduce something which is more Bohmian. So he's introducing the principle of outcome independent from later measurement, Bohm. So this is also quite intuitive in Bohmian mechanics. So when the hidden variable theory is applied in a reference frame F, then the outcome of a measurement Q made at time t does not depend on the choice of what is measured at times t later than t, viewed in the same reference frame, even if these later measurements are made in a region separated from the region in which measurement Q is made by a space-like interval. So this is quite intuitive in both ways. The first one is summarizing some idea about Lorentz invariance. The dynamic should give the same result for every reference frame, Lorentz reference frame. But the second principle is giving you a kind of causality from past to future, and also is allowing non-locality through let's say, faster than light signaling. So what is the consequence of that? You can imagine quite quickly that we'll have some problem when you combine these two axioms. So this is the theorem, the derivation of Nicolas Gisin. So what he's doing is considering again two galaxies, Alice and Bob in both galaxies, and then one is measuring one of the particle alpha and the second particle beta, and they were coming from the same source of entangled particle, let's say. So it's a singlet particle, for example, singlet pair of particles. So one is when the particle is getting the outcome alpha, the second one is getting the outcome beta. And then you have non-local link between them, and you can watch the program from the point of view of two reference frames. In the first one, the foliation F, your Bob is measuring before Alice, and the second one, F prime, Alice is measuring before Bob. So now what is happening? In the case of the foliation F, so Bob is measuring before Alice, so the hidden variable should impact the dynamic in very specific way. So if you apply Bohm in this reference frame, the result beta measured by Bob should depend only on the wave function, on the settings at Bob's side, and also on hidden variable for Bob and let's say the source of the particle. The second outcome, alpha, should depend on everything. So it should depend on Alice, Bob, and all the hidden variable, because you can have non-locality, not instantaneous link between them. But now, if you watch the same thing in the different reference frame, F prime, so the role of Alice, Bob, and alpha, beta are somehow inverted. So everything now is looking differently. So for example, alpha is only depending on the Alice parameters, and Bob and depending on everything. And now you see the problem immediately, because when you combine these two axioms and then you use the principle of Lorentz invariance, you will deduce immediately by watching this one, then alpha and beta are local parameters defined by the hidden variable of the source and local settings. But you know from Bell theorem that local hidden variable are violating Bell theorem. So this is prohibited. So you see that assuming these two principles together, you have a contradiction. So it doesn't work. So what does it mean? I mean, you can illustrate this even more with an example, the RD paradox, which was published by RD a little bit in the same time in his previous paper. So you have the non-perfectly entangled state, which is written here. So you have two particle plus and minus again, positively charged and negatively charged. So you have a not perfectly entangled state here. Everything is one term is missing in this state. You see, there is no a plus and minus state. So you can have everything else. And now you suppose that Alice and Bob, located in remote galaxies, are applying or not applying unitary gate, beam splitter, which is represented here. And it can split the wave packet in a natural way. For example, if you have a superposition of V plus, A plus, then you are going to C plus here. And if you have A plus minus V plus, then you're going to D plus. So it's a natural gate. And what you can see is when you compute the things with the unitary evolution is that at the end, the probability to have D plus D minus is not equal to 0. So you have one probability, not neglect, you cannot neglect this probability at all. So it's important to remember that, 1 over 12. The value is not really important. And then now there's a paradox, because imagine that you apply some locality principle. So Alice could decide not to put his Erbil splitter. So then you can derive the following things. You can see the following things. So imagine that the particle is in V plus. So you see that V plus has two possibilities, this one or this one. You can make the superposition, A plus plus V minus. And this will give you immediately C minus. This is in obligation, is a necessary consequence of the evolution. But the opposite possibility, if the particle is in A plus, then you have the V minus, and V minus can evolve into V minus or C minus. So the only way to have D minus is to have the particle originally in A plus. So this is represented in this slide here. If you have D minus, you have A plus. And this is symmetrical. It means that if you do the same thing with the other part of the way around, so if Bob is removing his beam splitter, you deduce an D plus implied a minus. This is summarized by these two conditional probability here. And now you have a contradiction, because I told you before that PD plus, PD minus is not equal to 0. And then it means that in those cases you have necessarily this condition, D plus, D minus imply A plus, A minus. But I told you before that the wave function doesn't contain A plus, A minus. So you have a contradiction. And this is the RD paradox. And the RD paradox is solved when you remember that you have assumed locality. So if you remove this assumption, then you don't have contradiction. And actually, if you watch this from the point of view of Bohmian mechanics, you have a curious feature. So if you watch this from the point of view of the foliation F, where Bohm is measuring before Alice, the only possibility for having D plus and D minus is that it's this one. So the trajectory are following this kind of path here, okay? I can derive it if you want, but it's quite simple to understand. And the same symmetrically for D plus, D minus, if you watch the other reference frame. And this, of course, completely different. So where is the problem coming from? Of course, the problem is coming from that the two reference frames are different, and you cannot apply the Lorentz invariance framework together in both frameworks. Another example which is nice has been discussed by Jean Bricmont in his book Making Sense of Quantum Mechanics. So you take a singlet, here a pair of particles of spin up, spin down, and then he discussed that in his talk. You can see that on YouTube. And if you have Bob is measuring before Alice, so and if the two particles are located in the upper part of this wave packet here, so the symmetry of the wave function tell you necessarily that the particle has to go here means a spin up. But then from the anti-correlation, the other one has to be spin down. But now, it is Alice which is measuring before Bob, so if you're watching from the different reference frame, then you have the opposite conclusion. So, the Alice should get necessarily this one, the plus spin, and this one, the negative spin. So this is, of course, very strange, and this is coming again from applying Bohm mechanics to different reference frame. So what is the solution? The natural suggestion is to use a preferred reference frame. So this is very, very strange. So of course, you could imagine to see, maybe we can determine this experimentally, but this is hidden because I told you, I cannot enter into detail, but there is the no signaling theorem, which is prohibiting to use hidden variable for transmitting faster than light information. So imagine a Bohmian daemon, which is watching the hidden variable. Then this Bohmian daemon will have access to this information. It could determine which foliation is the good one. But in order to do that, he has somehow to break the Bohm rules, or somehow to use a non-quantum equilibrium regime, like Valentini would like to find, for example, in all the stage, first stage of the universe. So these are some conclusions taken from Hardy, Gisin, and also from Conway and Cohen. So some of the conclusion of the theorem is that the hidden variable theory are not Lorentz invariant. So this is one possibility. Another possibility, which is much more radical, there is no such at all. There's no such covariant hidden variable theory. So in other words, this is the reason why they call that free will theorem. There is a causality which is somehow dominating the dynamics. So somehow you have genuine randomness. I think it will be the picture favored by Gisin and Conway and Cohen. And another solution could be to prefer reference frame, so some kind of Aether. This would be the point of view of Bohmian mechanics, let's say, of most Bohmian. This is indeed very strange because it suggests the revenge of the Aether. So the Aether was introduced in the 19th century, and you know that it was a strong debate between people like Lorentz and Einstein. So because it's some kind of hidden variable of the 19th century, but now you see that Bohmian mechanics, and many people in Bohmian mechanics, starting with Bohm himself, Vigier, which was a collaborator of de Broglie, John Bell, and the more contemporary people like Anthony Valentini, Zanghi, Deterministic, and Sheldon Goldstein are always assuming this kind of picture. But this, of course, favor a kind of prefer reference frame, so which is very, very non-relativistic in some way of thinking. Still, let's say what John Bell say about that. So it was written in a nice book in the 1980s. So the motivation for Bell is the following. The reason I want to go back to the idea of an Aether here is because in this EPR experiment, there is the suggestion that behind the scenes, something is going faster than light. Now, if all Lorentz frames are equivalent, that also means that things can go backward in time. And it introduces great problems, paradoxes of causality and so on. And so it is precisely to avoid this that I want to say there is a real causal sequence which is defining the Aether. So this is very clearly precise here. But of course, you can ask if it is the only solution. And what about the serious Lorentz invariance? That was John Bell was worrying very much about this topic of serious Lorentz invariance. So here I'm going to be very speculative about this issue. I would like to go a bit beyond the idea that we can have a preferred reference frame. So imagine that you have, again, quantum experiment, you have several particles which are entangled, and you have a foliation which are defining in Bohmian mechanics the dynamics. So you do the experiment once, and if you are a demon, you can observe this kind of dynamic. Precisely, you are not limited by no signaling, let's say. And if you do it again in a second time, maybe you reproduce the same condition of the experiment, and again another time, maybe the foliation will not be the same. It doesn't mean that you don't have the same medium, but somehow the connection between the particles are different. What I'm telling here is that the foliation could maybe represent some kind of dynamical connection between the particle, which is not necessarily associated with the medium. So it will be more nomic in some sense, more nomological than the connection that people think about as a medium, as an Aether. So what it will imply is that it will imply that you have a new Bohmian framework where you have to add to the wave function in discussion the foliation, and then you can ask if the foliation is on either or not a part of the dynamic or the primitive ontology. This is something which would be nice to discuss. But the foliation has no dynamical role, so it's representing the connection between the particle, a synchronization between the clocks of the particle, which is fundamental for defining the dynamic. But you could also imagine a second kind of foliation, a second kind of foliation that are associated with the observer, which is not taking part of the entanglement, and which is unaware of this process associated with this foliation. And for this observer, the thing could be very different. And now, this Bohmian framework is a bit different because you have a distribution of foliation. So it means that you could imagine that all your hidden variables are depending on the foliation and the hidden variable in the wave function. So the parameters, the outcome of the experiment alpha could depend on psi of the foliation and the hidden variable. but you have a statistical distribution of foliation. So at the end, you will average on all this foliation and you will obtain the same result that you have in an orthodox quantum mechanics. At the end, it will be empirically equivalent to orthodox quantum mechanics, and the foliation are hidden, like the hidden variable lambda, because of no signaling theorem. And this will be somehow weakly in agreement with the Lorentz invariant, the Lift proposal of RD, because now you have a kind of foliation democracy. All the foliations are playing the same role, but you are not really maybe a serious Lorentz invariant, but it's maybe the better that you can have in an instance of Bohmian mechanics. So the foliation is a parameter, but it's not a fixed parameter. So an example of possibility would be to use the so-called multi-time Dirac equation. So it's called the EPR surface Bohm Dirac model, which was developed by Deterministic and collaborator. And it was based on previous work by Bohm and Néel and many others. And so the idea is that I don't want to enter into the detail because it's technical, it's not really relevant, but the point is that you have this wave function for the spinors and entangled particles, and you can define precisely the dynamics for the path of the particles, but it's foliation dependent. So if you change the foliation, you change the direction end of the photo, you get different dynamics. But all the dynamics are low because the foliations are simply, all the foliations are possible. So imagine now that you have one of these foliation F0 and you watch it from the another one from the laboratory reference frame. Then if you will have access to hidden variable, you will get something very strange because we'll have a kind of time machine. You could influence the past. Because if you have a foliation F0 like that, which is where Bob is measuring before Alice, and you see that the outcome by Bob will influence what is happening at Alice settings, but from the other reference frame point of view, somehow it will be looking like what is happening in the future is influencing what is happening here. And indeed, you can show some simple example. Take, for example, again, this EPR quantum states here, and this path which are crossing or not crossing. So you see, I remember this before. And now imagine that before, instead of putting a mirror, I put some trap here which are trapping the particle before that they're crossing. This is done by Bob, and so Bob can do either this or this, okay? And this, of course, influences non-locally the trajectory on Alice's side. But from the point of view of the laboratory frame, it will be like a time machine because you can compute the conditional probability for different outcomes, and you will see, for example, that the probability for obtaining D plus, knowing that you have A plus, it's 1 in one case and 0 in the other case. So it's and this is determined by something which is happening later. So you have a very strange causality paradox happening here, but it's not really a paradox, at least for people like us, because everything is hidden by no signaling, and also it depends on foliations. So if you change the foliation, you can have different dynamics, and on averaging of all this foliation, you have also averaging all these things together. So there's no causality loop, I precise, because you have to choose one foliation for determining everything. You cannot mix different foliation. So one foliation is doing that, but you cannot mix with the different foliations. The foliation is part of the dynamic, but is part of the rule of the game somehow. So with that, I would like to finish with some paradox associated with Wigner Friends paradox, which is very nice thing which has been discussed recently by Renato Renner in particular, and this is becoming part of the folklore to discuss about this Wigner Friends story. So you know what it is about. It was introduced historically by Everett in his PhD thesis, but it was coming from the lecture of Wigner. So Eugene Wigner. So you have two observers, F and Wigner, which are observing one another, and there's a quantum system, spin up, spin down, and you see what happened when the first system, the first strand is observing the spin, so it's getting entangled, and then later the Wigner himself is getting entangled. So you have a propagation of entanglement to larger and larger systems. So it's to say that the shift is split, somehow of the quantumness is moving, is propagating. this is like that people are discussing this in a normal framework, but for people like Everett or for Bohmian, this is very problematic, and this motivates ontology. Okay? And no, what did Renato Renner and Daniela Frotschiger in a very nice paper published in 2018 is to use this kind of things together with the Hardy paradox. We didn't explicitly call that like that, but actually when you analyze it, it's connected to the Hardy paradox, because you recognize immediately the same quantum state that I introduced in the Hardy paradox before. You have a not perfectly entangled state, and you have a coin which can be head or tail, and a spin which can be up or down. Okay, and they are in different labs are located far away, for example. And now you have two friends, F and F bar, so the two laboratories are called L bar and L. And you have two friends F and F bar, and also two Wigner, Wigner bar and Wigner. And this Wigner can make different experiments. They can observe in different bases. They can decide to observe in a original basis, which could be head, tail, spin up, spin down, or they can use this again, this unitary gate like before. You can put this OK and fail, or OK bar and fail bar. This was used in an article of Renato Renner. But Renato Renner also introduced curious things, because he introduced something like, I would call that the Dutch erasing procedure. So you have a friend that is participating to the experiment, but he has to erase this information somehow before to leave the lab. Because if it is keeping this information, it's like a witchpath experiment. You will have an information that you can give to Wigner, and then it will break the coherence of the wave function. So you can erase the information, but you can erase partially the information. You can only say, okay, I play. And the other one can do the same, I play, but he doesn't remember what he did, but he played, okay? So already something that is minimal information. So now you can reproduce the reasoning of Daniela Frotschiger and Renato Renner. I mentioned that I discussed this topic in the context of Bohmian mechanics in a paper in a recent year, but there are also two nice papers which are related with different perspectives on Bohmian mechanics, which are by Siberian, Justin Dorici here, which are very, very interesting also, and which are related to my perspective. So so what is the Hardy paradox in that context? So imagine that you have this state. So imagine that you have you have tail here. Okay, so if you have tail, you have the superposition spin up, spin down, and this means that we will have fail if you apply the unitary gate of the defined by Renner. But now, if you have the head for the coin, then you have to have spin down. But spin down can split into OK and fail. This is again the property of the unitary gate. So you see that the only way to have OK is then to have head. So the coin must be head. This is a logical inference. And symmetrically, again, using this quantum states, you deduce that if you have OK bar, then you must have spin up. This is necessary. But now, like in the paradox before, you can deduce easily that the probability for OK bar is not equal to 0. And you get a contradiction, because the wave function psi here doesn't contain the spin up, the spin up and the head. But these two logical inference would imply that you have to have spin up and head. You see? So you have a contradiction. And this contradiction could be also obtained in a different way. Imagine you have OK bar, then it will mean that you will have necessary spin up, then it will mean that you have necessary tail for the coin, then it will mean that you have fail. And though you have this implication OK bar means fail, but this is in contradiction with this. This is another way to see the paradox. So this paradox is coming it's the Hardy paradox, and it's very strange because of course it's related to the fact that you use different Wigner friends, and it seems that you are breaking the coherence of the wave function. If you want to have the friend want to share information, you will get in contradiction, because you see these different people here has to share information. Otherwise, it's staying in some kind of bubble that they cannot participate, they cannot share information. But if you apply a rigorously quantum mechanics, there is no paradox at all. So I want to say that by proving it using Bohmian mechanics. Bohmian mechanics is a framework which is applying which is applying the ontological model to both partners, so to all to both labs, and all things should be consistent in one picture. So the thing is that Bohmian mechanics require foliation. So imagine that I use the foliation F0 to compute the path. So what I will show is like in the paradox that I illustrated before, is that necessarily if you have OK bar and OK, the spin should be proper in a state up before, and the coin will be in the tail here. So this is again a logical inference. But if I use a different foliation for determining the dynamic, I will obtain a completely different conclusion. And the difference is that in one case, F bar is measuring before F, and F then is measuring before F bar. This is from the point of view of these two foliation. I precise that this is observed from the point of view of the foliation F0 and F0 bar, F0 prime, but from the observer in the lab, which are using a common foliation, common time, this is invisible, okay? This is hidden. The thing is that at the end of the process, everything is erased. Don't forget that the observer is erasing this information. So you have no way to see this. It's hidden again. And there is no contradiction if you respect the rules of quantum mechanics and if you use the good Wigner bubbles, to call it like that, in your discussion. And no, this was the sketch coming from my article, and you see it was using the conclusion from this framework. Yeah, I have OK bar and OK, and here the observer is observing tail. This is corresponding to this, and this one is observing spin up, and then at the end is erasing this information. I say only I play. There is no problem. But now, what happens if there is not erasing? If this guy is not erasing, then you are sharing the information with the outside world. So he could share the information with this guy, for example, and then you could get contradiction. The only possibility is then that non-locally the things will be different. You will have this conclusion that I observed before in this logical inference here, okay, or this one. I mean, if I have this, then if I have OK, I mean that I have necessary to have head here. This is a necessary link. And there is no contradiction again. These two dynamics here and here are very different, but you see they're not using the same protocol, so they are contextually different. Well, now, what is the conclusion of my talk? There are two or three conclusions. The first one is that we could imagine a kind of covariant or semi-covariant framework for Bohmian mechanics, which is using the wave function and the particle, but also the foliation. So you could discuss about the nomological status of the wave of the foliation in this dynamic, but anyway, it's representing a kind of connection between the particles. So it's a synchronization. You could allow a distribution of foliation in the same experiment, so you are not able to say which foliation is happening in the actual run of the experiment, but you can, from run to run, you can have many foliations happening, and many synchronization if you want. And everything is hidden because you have no signaling. In this picture, retrocausality is allowed, but it's difficult to control because you have no signaling theorem, which is connected to some kind of quantum thermodynamic, let's say. And if you want to observe that, you have to break no signaling, so you have to break quantum equilibrium. So it's connected to the work of Anthony Valentini, for example. And you can discuss, as I said, the role of the foliation in this ontology or versus nomology. But the Lorentz invariance is not perfect, of course, because you have still even though you have a foliation democracy, this is somehow non-local. It's not really like the picture that you would like for a Lorentz invariant system where it's only local light cone which is defining the dynamic. But at least it could open very interesting discussion for cosmology, for example, because you could imagine that the distribution of foliation is connected to boundary in the earlier stage of the universe. Maybe the foliations, the distribution isn't completely arbitrary, but maybe the cosmology then will define this between different regions of space. So if you have a Big Bang, you can imagine that there's a kind of preferred foliation which is dominating the distribution, like a Dirac peak in the distribution of foliation, but it's not necessary, something which is very peak at least. But if you have no Big Bang, you could imagine, for example, a big kind of big bounce. These drawings are coming from books of Roger Penrose, so you can imagine things very strange. You could imagine the distribution of foliation, it will survive afterwards, but you will not be able to favor one foliation. I think they will be all surviving. And in quantum gravity, this could also have some consequence, because I told you generally that the wave function is generally considered as a homological object. One of the motivations is associated with the work of Duo, Goldstein, Zengi, and many others concerning the universal wave function, the conditional wave function, the effective wave function that you can take from this. So imagine that you have two coordinate, two particles, let's say, one, if you solve Bohmian mechanics, one can be used for, let's say, defining an effective wave function for the first particle with respect to the second one. And in quantum gravity, this allows you to imagine a picture where the time is emergent, because, for example, if you use the Wheeler-DeWitt equation, when it doesn't matter the structure of this Wheeler-DeWitt equation here, you have an operator acting on the metric, another operator acting on the material field, for example, a scalar material field. The wave function here is independent of the time, so it's because you have to have some kind of diffeomorphism in invariance. So there's no time really happening in the structure, but the Bohmian mechanic is making the time explicitly appearing, because you have it's important to have first order the time derivative. So you have dynamics, and in cosmology, for example, the metric is quite simple. You have a parameter in the Robertson-Walker metric, which is the scale parameter. And you see that now you have two fields here, the A, which is defining the space, and the phi, which is representing the matter. And if they're all both depending on time in a not too deep, complicated way, you could remove the dependence. For example, you could say that phi depend on A or I depend on phi. So the time is very emergent in some sense, and that's the picture. The matter could define the time, or the space could, excuse me, the space-time could define the time, or the matter could define the time, but this is relative picture. But in Bohmian mechanics, this is foliation dependent. It means that if you use a different foliation of space-time, you get in principle different dynamics. So it's not completely solved either. So again, this discussion about the foliation is surviving. And so the reason why I think that it's important to take into account this discussion about foliations and the possibility to have a foliation democracy in the theory. And now my last slide is to thank you first about not being bored today. And I would like to finish with this quote of Louis de Broglie, which was an answer to Laurent Rosenfeld, who was criticizing David Bohm for publishing a book, Causality and Chance. And Louis de Broglie has to reply officially in journal Nature to say that in these conditions, it does not seem to me justified to condemn a priori the effort of those who try to take a new point of view and to obtain an image of the physical world more intelligible than that based on the conception of complementarity, which remains, in spite of everything, rather obscure. So I think I would like here to conclude and to thank you for listening. Yes. Thank you.
Thanks a lot, Aurélien. Very nice talk. Okay, so questions, as usual, either you raise your hands or write your name down in the chat. Okay, I have a question from Ward, then one from Jan, and let me see the ends, and Lev. So Ward first, then Jan and Lev.
Hey, thanks for the nice talk.
Wow.
So I have a question about this distribution of foliations.
Yes.
So I understand. So like one way to formulate Bohmian theory in Minkowski spacetime is to say there's one particular foliation. Okay.
Yes.
And suppose I have n particles in the universe, then the dynamics for these n particles depends on that foliation. But now I don't quite understand what you're actually proposing, because I don't see room for more than one foliation. Okay, so
yes.
if I'm thinking on the universal level, there's just one foliation of space-time.
Yes, this is always the question that in fact, it's always difficult for me to explain that. Thank you for the question. So the point is that I mean, it was this picture is trying to explain it. This is an experiment made in one lab. Okay, imagine you have one lab which is making the experiment and is observing this. Normally, if you what you are doing in Bohmian mechanics is to assume that when you repeat the experiment again and again and again in the same lab, the foliation is chosen, is fixed. So
okay,
here,
but hang on. So if I have the usual dynamics with one foliation, if I repeat the measurement, okay, so that's going to be at another region in space-time. And of course, even sticking with one foliation,
yeah, you're right.
the form of the foliation might change, right, from one region in space-time to the other.
You're completely right.
Okay.
You're completely right. It could be this. It could be the evolution of the foliation, but then it's very strange because normally, if you think about space-time in a flat space, locally it would be flat, so you will not expect necessarily that the foliation is fluctuating. Here, I'm not supposing that this is a medium which is fluctuating because, for example, in your work, in some of your paper, you mentioned that it could be the foliation could be determined by some current or tensor, which is determining the dynamics. Okay, and then some kind of preferred reference strength. I saw that also in the paper of Detlef but we could imagine that it's not at all the case, that maybe the foliations are defined by something else that we don't know, which is the synchronization between clocks. But I will call that some kind of new hidden variable.
But it could be curved too, right? So that's what I'm saying. And so in one region of space-time, it could be completely different than another region of space-time.
So it's simply to add another degree of freedom in a theory. But,
okay. Yeah, I see, but like I just still don't see how you can have more than one foliation of space-time. So take the whole space-time. Are you saying there's more than one foliation of the whole space-time now, or just one?
Yeah, exactly. In the same place, you could have different foliation. There's only even if it's different time, of course, because when you do the experiment you do it not in the same place in the same time. You have to do once and then a second time and a third time, etc. But normally, the foliation that people are thinking about is a kind of dynamic medium. Okay, and here I'm telling that it could be synchronization between the particles. So it's like a law. It's not a fluid which is imposing it's not space-time himself which is imposing the foliation. Okay, it's not you don't have a fundamental structure which is necessarily imposing the foliation. The particle were prepared initially in order to have this connection here. But this is not a structure which is like in standard Bohmian mechanics in quantum fields. People are using this foliation and really watching it as an Aether. So it's maybe it's a bit metaphysical as a definition, but it could open different perspectives because for me, for example, I would not accept the idea of Aether, and I would like to suppose that these particles are connected by something else. So I would like to build a genuine Lorentz invariant theory, but then it will have to go beyond Bohmian mechanics. So I will suppose that the links between the particles is based on something else, maybe some retrocausal dynamics or superdeterministic dynamics, but something else. But I don't want an Aether. So the framework is here only to discuss this possibility.
Okay, thanks.
Next one is Jan.
Yeah, I'm not sure I have something to add after Ward's question, because I'm a bit confused about what these foliations are supposed to achieve. Maybe you can say a word or two about that, because of course, if you allow retrocausality, then of course I don't know what it means to be Lorentz invariant, I mean, it seems to me, of course, if you have non-locality, if you have non-local action at a distance, and you have retrocausality in certain frames, that's unavoidable. But of course, you could say that there is a true frame in which real causality occurs, and that would be the preferred frame. That's how I understand things. But I don't see why these, well, first of all, continuing towards question, I'm not sure that you have very different foliation of space-time. You may have different local foliation depending on when you are in time.
My motivation is coming from the Wheeler-Feynman theory. In Wheeler-Feynman theory, retrocausality is allowed because you have time-symmetric dynamics. So you have action at a distance, but is not is not located, is not going faster than light. And you can, if you remember the history of quantum mechanics, one of the motivations for retrocausal things in quantum mechanics discussion was the work of Costa de Beauregard, and Costa de Beauregard was thinking about wave going from future to past. And he was discussing with the Broglie about that. We thought it was completely crazy. But the idea is still somehow discussed nowadays in many different frameworks. And I know even some proposal of non-local hidden variable by Sutherland in Australia, which is trying to use retrocausality in Bohmian mechanics in some framework as well. I think Valentini also writes some paper about it. I think it's possible to imagine a dynamics which could be retrocausal. So this is not a fatal objection. But I wanted to stick to the standard quantum Bohmian mechanic picture, and without adding the thing that they are adding in their new Bohmian dynamics, because this is not really what they are proposing is really unorthodox Bohmian dynamics. Let's say you need a two-time boundary condition, something very strange. I simply use the normal Bohmian mechanics. Okay, but the thing is that I want to simply assume that there is no Aether. It's only that, the point. It's only that. So there is no Aether, so it means that the connection between the particles should be found in somewhere else. And I suppose that there is an underlying dynamics which is more sophisticated, which is beyond this Bohmian framework, which is explaining this. I could not enter into the details today because it would bring me way too far, but this is to be for another topic and discussion, but it's possible to create this kind of dynamics. So if you do that, then it will explain this kind of framework as a kind of a structure which is coming afterwards, superseding the Lorentz invariant framework. So
you're saying that these foliations come somehow naturally, and they are not.
Yes, they are finding a more fundamental explanation at the end. Here, I simply assume that they're representing, you see, some synchronization procedure. I don't want to enter into the physical explanation of that, but the particles are synchronized. There is no medium which is synchronizing them. They are synchronized because of the information coming to the particles before. But this synchronization is not due to a preferred slicing of space-time on different lines.
Okay. I don't quite understand, but that's okay. That's okay.
It's okay. Okay. I think we should discuss this more.
Well, we can come back to that if we want later. Let me see what Lev and Nicholas wants to ask first. Lev, you're next.
Okay, thank you for the talk. I read the title, and the title kind of saying we have this Bohmian mechanics and we have retrocausation, or what I understood that can you think about Bohmian mechanics when you have both information from the past and from the future? And I was trying to understand what it might mean, and I never was able to even think about what it is. For me, what's hidden variables theory tell us? We have quantum mechanics. Quantum mechanics, sometimes the standard quantum mechanics doesn't tell us what will happen. And if you don't want to believe in many words, and you want to believe in one word, then there is kind of hidden variables which will tell you what really will happen with your situation. But if you have future information, so you know what will happen. So what's the point? Maybe still the both information in the past and the future will not always fix your Bohmian trajectory. Frequently it does. Sometimes it doesn't. But why would I need them if I already know what's going on? Why should I? Why it's interesting for me? So my first question: what this kind of two boundary condition hidden variable might achieve? Why do we need it?
Oh, we did not so much discuss this framework, but you know it.
But let me just ask two questions, and then we'll. decide what.
I think I can answer because I like anyway the proposals of Sutherland and
what?
I mean, Sutherland in Australia, I think he wrote a few papers about this proposal using something that looking like a two-time boundary dynamics. You know, you have two waves, like in your theory. You wrote many papers about this idea where you have one wave going from past to future, and the other one going from future to past, and you can imagine to build Bohmian mechanic with these two waves. This is completely possible.
What is Bohmian mechanics is hidden variables theory.
Yes.
Tell me what will it adds to standard quantum mechanics, and tell me what will be the result of measurement. So I don't understand what if I know the future result of measurement. So I don't understand what it will give me.
It's like weak measurements. You know, weak measurements is actually, you know, that Bohmian mechanic is related to weak measurements. So in this the proposal of this guy, it's the idea is that if you have the wave function from the past and the wave function from the future, you can define that in intermediate time quantity like the velocity of Bohmian mechanic. You know that in Bohmian mechanic you need always this kind of picture. Here you have yes, it's written here, but you need it's not so clear. You need the wave function psi and psi conjugate to define a current, but you can also define a current or velocity with a psi, the two wave function psi coming from the future and psi from the future.
I'm sorry, just never mind how you defined the trajectory. Why it's helpful? Why do you need it? What it's good for?
It's good for defining a dynamic which is completely Lorentz invariant.
What? But when you have pre and post selection, what is Lorentz invariant? When you already know what is the future, how you can talk about Lorentz invariant? This is Hardy's paradox. Hardy's paradox saying that there are no covariance theory, whatever. He was mistaken because he was thinking that there are elements of reality given pre and post selection, and there are no elements of reality given pre and post selection do not have product rule, which he used, so there is no paradox. So there is no
This is an answer, of course, but this is not the answer of Bohmian mechanic. The Bohmian mechanic is more critical about that. He will say that the observables are defined by precise contextual measurements. So if you have a measurement, it's by outcome at the end, it doesn't mean that you don't have a reality between the preparation and the measurements. You are completely allowed to try to build a dynamic which is completely Lorentz invariant between the beginning of your preparation and the end. But the theorem of Gisin and many others is telling you that it's very difficult, and so that's the point. But the goal is fine because it's interesting. And no, the theory of this guy Sutherland and Valentini is different because they're changing the rule of quantum mechanics. They're using these two-wave functions. This two-wave function is not exactly the same framework. So I think that if you try to analyze this theory in the framework of maybe the Gisin theorem, maybe we get something else. But I didn't think about it honestly. Yeah.
So maybe just raise a second worry, which is more or less the same like Ward's worry. We have Bohmian mechanics, which many like about it, and I also like about it. This is complete theory. It tells us exactly what's happening. I give you initial conditions, there are laws, we know everything. There are complete equation for everything. Now, it's not Lorentz invariant, and then you can say maybe it's a good argument for preferred Lorentz frame. Preferred Lorentz frame is particular foliation. So then it's also make it kind of at least artificially Lorentz invariant, because you know exactly what's happening. I don't know, it's not hard to say it's Lorentz invariant when you have preferred frame, but then you have complete theory, you know exactly what happened. Now you add this foliation, which is not clear, and when words try to ask you hard question and others, I don't see any equation for this foliation. You don't have a theory.
No, I don't.
Like you are looking for a theory.
I'm looking.
And for me, I think that there are interpretations of quantum mechanics, some of them bizarre, maybe, but I think one should consider. I think if one has a interpreted new proposal, if it's kind of finished proposal, then it has a right to exist. And one can ask if it's strange, not strange, if it's better than others. But just to say, let's look for another proposal without presenting them, this kind of thing, I don't see, we already have on the market many proposals which are kind of complete proposals. Maybe some people like them, not like them, GRW, whatever, but they are definite theories. They tell us exactly what's going on. Now, to present something which is say, okay, I don't like this, maybe if I'll go to this direction will be another proposal. If I understand, this is not more than this, or you have something more than this.
I think there are two different things to say. Okay, maybe if you will assume what you say about the not need for another theory, then probably GRW will not exist, and maybe even Bohmian mechanics will not exist, because they will say, okay, everything is fine already. So it's not. This is not the point. But what I have two things. First, to say that you could axiomatize the framework like normal Bohmian mechanics. I mean, Bohmian mechanics is using a wave function and is using the Bohm rules as a condition, which it could be connected to typicality, for example. And this is, you can define a rigorous framework for justifying that the density of probability is psi square. But now here I'm telling you, I don't have necessarily a theory for foliation, but if you say, why not to have a Lorentz kind of democracy for all this foliation, then you will put kind of natural homogeneous distribution, and then you will have a theory which is fine as well. So it's possible to axiomatize the theory in such a way that you have some symmetry. So I don't think that it's really problematic. But the real goal is to go beyond Bohmian mechanics. Honestly, my real idea is to go beyond this non-locality. So then it will be something else. But before to do that, I would like to assume that Bohmian mechanics is true as a kind of, let's not say approximation, but it's true as a coarse-grained picture when you watch only the trajectory of the particle. But if you watch more in details and you zoom on them, you will see something more complicated. That was already the picture of Bohm, by the way. And yes, I'm trying to find a dynamic of that kind. Yeah.
Yes, I heard from Bohm that he never considered his theory as the final theory. So
yeah,
I agree with you. Okay, thank you.
You're welcome.
Nicolas?
Yeah, so bonjour Aurélien. Thank you for the presentation. I have one comment and one question. The comment is on your slide where you cite John Bell.
Oh yeah, yes, this one.
This one, exactly. And so he is saying that, okay, Bell is saying that suggests that behind the scenes something is going faster than light. Actually, Bohm in his original paper also wrote something like that and suggested maybe this thing that goes faster than light goes at a finite speed. Of course, in Bohmian mechanics, it goes instantaneously. And just the comment is that with colleagues, we considered that and could prove that anything that would go at a finite speed, finite but faster than the speed of light, would necessarily lead to signaling. The only way to avoid signaling is to go instantaneously, so infinite speed, which I think is an interesting addition to this slide here. But that's just a comment or a self-advertisement, if you prefer. The other one is about at the very beginning when you are actually talking about Hardy and my stuff. And so here you have this detail, okay, here somewhere. Yeah, so here you have these functions, FAB and FBA. So you have a function which just means it's deterministic, no? And you have it also in your title somewhere, I think. And okay, I understand that. But one thing I don't understand is why can't we not also make that for non-deterministic, non-local hidden variable? And here I have to say I'm very puzzled. For instance, if we go to GRW, what you could imagine other cases, which are non-deterministic, but at the end of the day, you have the stochastic process, a Wiener process, if it's in the continuous case, but you could have jump operators, you would still have some Poisson noise. So you have some stochastic processes, but any realization of any of these stochastic processes looks like a hidden variable. Of course, a non-local one possibly, but you have something which once a realization is given, it becomes deterministic. And so I don't see how one, because there are many people who try, for instance, to make a relativistic GRW. And it seems to me impossible, just exactly for the same reasons here. So I know this is not exactly your topic, you are more on Bohm than on GRW, but maybe someone else in the audience can tell me how one can hope for non-local, covariant, non-deterministic hidden variable. Of course, quantum mechanics somehow is an example of that, but there the randomness is of a very, very special kind. As long as we have these Wiener processes that we have in all these models, I don't understand how one could do it. Although there are many people who spend their career trying to do things like that. So does anyone, you or anyone in the audience here, have an answer to that question?
I thought a little bit about the GRW. I didn't think about the flash ontology because this is an attempt to make the thing completely relativistic. But I think a bit about the GRW framework. Imagine that I think that the same conclusion could be done that I use that for the Bohmian mechanic. I use different foliation in my framework. So we could imagine that again, one foliation is determined for any reason. Then non-locally, there will be a stochastic influence from Bob to Alice, or Alice to Bob. And if you do again the experiment, the foliation could be different, and then it would be Alice which would be acting on Bob, and that would be very strange, but at least it respects some kind of Lorentz, not really Lorentz invariance, I don't like it, but I prefer this symmetry, this democracy between the foliation, which is a kind of poor man version of Lorentz invariance, but it's still satisfying some symmetry between the foliations here. But I think it's possible to do that. But with the other proposals, maybe I need somebody else know more than me about the Tumulka framework, for example, but I didn't think about it at all.
If someone, there is maybe Lev with a finger there.
Yes, you know, the Tumulka really has these flashes which are at least artificially Lorentz invariant. But Nicola, if you consider GRW the original one, which was come from work of Pearl and the original GRW, and when the ontology is a wave function, then it cannot be relatively covariant because it has action at a distance. If you have a particle and a superposition in two different galaxies, then if you don't do anything, then the wave function will remain for a long time to be just this superposition. But you'll come to one galaxy and if you perform a measurement, you force the other one to jump to zero into another one. So there is action at a distance. If there is action at a distance, forget about Lorentz invariance.
So Lev, you're saying that I'm right with my intuition that at least the original or the mass density ontology, as people say, of GRW cannot be made relativistic.
Yes. For me, this mass density is the original one with a new fancy name for ontology. This is the original one, and it cannot be made relativistic.
No, that's not true. Please, I think that's not true. That's not true.
Yeah.
I can send you a link. Sorry, I can send you a link to a paper which does just that. I just have it on my screen here. So there's a paper by
Bedingham
et al. Yes. Bedingham, Dürr, Gherardi, Goldstein, Tumulke, and Zangi. And it's called Matter Density and Relativistic Models of Wave Function Collapse.
Yes, but this is without any interaction, isn't it? It's like the Tumulka model that prevents interaction.
That I'm not sure. I don't know. Maybe Wortstreif knows better about that.
No, it's a general framework. If you have a collapse theory of some sort and you want to add a mass density, it can be done in a Lorentz invariant way.
Even interacting.
Well, I don't know how much. So like for example, Bedingham has a relativistic model, right, for interaction. Okay, it's not formally rigorous, but at least you can add a mass density in it, such that the whole theory is Lorentz invariant.
Yes.
And the mass density changes along the light cone. That's the main idea.
I give you a very simple example. You have a particle, half here and half on the moon, and then you want to send signal to the not to signal. You want to change something in the moon. So one way you don't measure your particle here. Another way you measure your particle here. According to GRW, you put big device, a pointer, which will cause the GRW collapse necessarily, and it also will collapse your particle. So of course, if you look on, I don't know what, then the wave function on the moon, immediately after, very soon, not immediately, because you need some time for GRW collapse. But if you put many very big pointer, it will happen very fast. So very fast on the moon, the wave function from the half will go to 0 or 1. So just you can give me to tell me where I'm wrong.
No, indeed. So left, you're right. So the wave function changes instantaneously, say, but the mass density doesn't. The mass density gets updated or depends only along the wave function along the backwards light cone or something. And the example you're discussing, that's exactly discussed in that paper by Bedingham and the rest.
So the mass density is not just psi squared times mass?
Well, they look at it along the backward light cone, I think. So at one point, the value of the mass density is only determined by the wave function along the backward light cone.
So the
paper is now in the chat? So is that the paper in the chat, Christian, that you just shared?
Yeah, yes, bunch of papers, but this is the most recent one.
Okay. So then I'll take back about maybe it's not the original GRW. The original
No, it's not the original GRW.
But then, okay, so the statement that the mass density is the same like the original GRW, maybe, since I never studied carefully what's the mass density, maybe I'm wrong here. But
it's exactly discussed in that paper. That's the right paper.
But so who understands in this stochastic process? And isn't the realization of this stochastic process a non-local hidden variable? A deterministic, because now we're just fixing a realization.
What's non-local and stochastic?
Well, I mean, you take a realization of this stochastic process, a fixed realization. Now it's a fixed realization. It's like a hidden variable, a non-local hidden variable. And now because the realization is fixed, it's like a deterministic realization. No, it's realized. So you have only one. So what changes with respect to this result by Hardy and the others? Okay, I'm going to have a look at this paper, but for me, I'm very confused with this idea that by saying that something is stochastic, but actually it is just a classical probability distribution over realizations. So what is the difference? I don't know. But okay, thank you again for your talk, Aurélien, and everyone, for Lev and Watt for your contributions, and Christian for sharing that link. And sorry, by the way, I have to leave. I have an appointment now.
See you hopefully. I don't know. So so there's nobody else on the list. but so if you have questions, please let me know. Or if you want to go back to the previous discussion,
slide back because I switch off the slides.
So maybe I have a very silly clarificatory question on the nomological status of the foliation, Aurélien. Again, it's very silly, and probably I shouldn't ask you that. It's unfair to ask you that because at the end of the talk you mentioned that this is like something you have in mind, but about which is fair. I think, you know, it's a new idea. What I wanted to ask is, so I guess that this sort of inspiration came from the people that are considering the psi as a nomological feature in Bohmian mechanics. But so have you considered what are the differences between the two cases, and mostly have you considered whether some of the objections that people have against this idea that psi is
just a little bit, and I think everything is connected to the discussion that we had before, because if you consider the wave function as part of the primitive ontology, you will say okay, the wave function is a real object, and okay, and here I'm telling you that we can do the same discussion with the wave function, with the foliation, and maybe consider the foliation as a law, not as a physical entity. And this is suggesting different theory for the future. It's only this which is for me interesting, because one of the motivations for introducing the Aether by Bohm and Bell, when they introduced this idea about the Aether, and many others, they were inspired by the Maxwell mechanical medium approach. And you know that in the 19th century, everyone wanted to explain the existence of matter as something like vortex or dislocations in this medium, some kind of all is Aether point of view, let's say. And this was the whole picture of 19th century at the time of Kelvin and people like that. And this was clearly the motivation for Bohm and Vigier. We're working together on these kind of things, where they were imagining a subquantum fluid full of vortices, and these vortices are connected to this Aether, so to this ontology. So in this picture, the Aether has to have a physical status, of course, because you want to have a connection, instantaneous connection in one particular medium. And then other people like Paul Dirac proposed to have a more different perspective on the Aether, and he was using a distribution of particles like a thermal state, and he was telling maybe finally it's a bit different. You could have different foliations. So Vigier was, I think, working a bit on that. I don't remember the details, but you see if everything is about the ontology here, if you introduce the foliation in the discussion, you can imagine future theory. Maybe they will bring something else if you manage to develop a better theory than quantum mechanics. Otherwise, it's useless. I agree that, like with Lev, all the discussion about hidden variables are good. I mean, but we have already hidden variable model like Bohm dynamic platform to create a new one. But at the end, we don't know what is the future of physics. So this is open path. I try to think about the future of quantum gravity, about all these kind of questions. So this is the real motivation, is to go beyond Bohmian mechanics. So the nomological picture, anyway, is for me the temporary expedient. It's a very good way for axiomatic. If you put axioms, you have a clean way of writing your dynamics. In 19th century, people were also very pleased to axiomatize Newtonian dynamics, and there are a lot of papers about that, a lot of books and school, and fighting a lot about what is the most fundamental, the force, the mass, etc. And we know that everything at the end is a bit metaphysical. So my answer is that you have to wait. Maybe we'll get a better framework. It's good to have different perspectives on the same theory, because you know, it's like Richard Feynman said, if you don't have different perspective, you don't know, maybe one will make a progress, another one not. Maybe you will waste your time during your life working on one framework, which is very strange. Maybe it will be the case for me, but I want to try something else, you know. So
I share the methodology. I wasn't trying to.
No, I want to explain a bit because after the discussion with Lev, with Barb, and with Jean, I realized that maybe I didn't clarify this. I think I'm really thinking about a step further, not the next step, not simply Bohmian mechanics. Otherwise, it's only axioms, and yeah, I think I will not be able to answer. If it is only on homology, then yeah.
Yeah, thank you.
You're welcome.
Well, we still have some time if someone has one last question to ask.
Get bored. We'll go to the slide of Bohr.
Maybe I have a question, if I may.
Yeah, sure.
So Aurélien, and so what do you think of like the strategy of having a foliation, just a single foliation, but let it be determined in some kind of covariant way? Like, for example, let it be covariantly determined by the wave function.
Yes, yes.
Or by some other thing.
Yeah, I think that is it's a proposal as well. I think it's related to. It's not so different from what I'm telling. If there is something in a Big Bang which is defining the beta foliation, maybe it's connected to the CMB. Maybe it's depending on if you take the momentum of your fluid and for the different particle prefer reference frame by averaging, you have a good physical time for the universe. So yes, why not? But maybe it's depending on the model of universe that you are taking into account. And even with Big Bang, I'm not really sure that we are forced to use one foliation because, okay, you have the singularity, but the singularity is anyway a pathology. So if you take a big bounce, then it's more continuous. Then maybe there is nothing which is forcing us completely to have a foliation. I don't have a clear answer on that. But yes, of course, the possibility to have to define the foliation with the energy momentum, for example, or some current, it's very good. The X, I don't know, something like that. So, very interesting.
Thanks.
I think that's a finger from Lev, and then we have one final question from Ipo.
Word, it sounds like you want something like semi-classical gravity. When we say we take some expectation value and put it some constant metric depending on this expectation value, which sounds so ridiculous and so. You say you take a wave.
No, this is something else.
How you make a single foliation wave function has amplitude for different mass distribution. So you will every mass distribution probably will cause some foliation. So then to have one foliation for different mass distributions sounds completely against the spirit of quantum mechanics from my point of view.
Yeah, but so you have to look at the universal wave function, right? And you can imagine that there's going to be a map from the wave function to a foliation. And you can imagine that that map is covariant. So formally the dynamics would be covariant.
Semi-classical gravity, I can say covariant. They have Earth in this position, two places.
But I'm not thinking about gravity, right here.
But foliation probably related to gravity, otherwise.
No, it's just Minkowski spacetime. Okay, so it could be a foliation in terms of hyperplanes, or it could be a curved foliation, but no gravity, just Minkowski spacetime.
No, but that takes the center of mass of the universe and takes the Lorentz framework when its velocity is 0. This is your solution. That's all.
Right. That could be a.
Yeah, the problem is that we might be in superposition of different velocities. So then, what you will do then?
I don't know, but it's the wave function of the universe, right? It might be in a superposition. It will be in a superposition, most likely. So, but it doesn't matter. It picks out a frame of rest, right? Yeah.
But taking expectation value as something constant, I think it's ridiculous. Not ridiculous. It's my prejudice.
No.
But it's not in the spirit of quantum mechanics.
Yeah, yeah. Or in the spirit of relativity. Yeah.
A lot of speculation at the end. So it's true that if your foliation is determined by something more fundamental, so if it is determined by the wave function, so at the end it's not an independent variable anymore. This is a possibility, but so it's the reason why I wanted to explicitly consider the fact that the foliation could be independent and not necessarily fixed by something else, and to see what to do with that. And I like the idea that it's creating kind of foliation democracy, and that there's nothing to force us which foliation could be the good one, in the same way that nothing could explain which particles, why the particle is taking one initial condition or other one. It's not so different for me from what is happening in the quantum equilibrium. It's another kind of quantum equilibrium for foliations. It could be a possibility. Yeah.
Foliation democracy. Then maybe you'll calculate your Bohmian trajectory for every foliation, and then make some averaging, and
Yes.
you'll this is kind of a proposal for a theory. I don't know democracy or not democracy, but then it's a theory.
But this is the
Theory.
what I wrote.
This is what you have.
Yes, this is the idea. It means that if you take average of the foliation, you recover the same quantum equivalence, because empirically it's impossible to distinguish that from the standard quantum mechanics. So you recover Bohmian mechanics because each foliation is independently recovering quantum mechanics. So if you average on the foliation, you also recover quantum mechanics. It's not adding anything new. It's in that sense, it's quite obvious. So it's like a thermal state on foliation somehow.
But your averaging on foliation is mathematically not so simple procedure.
No, it's not simple procedure. It can be pathological. I discussed that in paper, but it can create problem, of course, because of this is the problem when you define a Dirac, for example, distribution in a Lorentz space, or things like that. You have the light cone, and you have a. This was discussed already by Dirac, by the way, and Jean-Pierre Vigier. And so this isn't. I don't have the slide here, but this. You can read my paper, or I can discuss. It's, I think I introduce a bit of information about that.
So I just kind of, this is my first question. I said that you have kind of idea for a theory. You say you have a theory. You say this is what you should exactly do. So you have.
I have a theory, but it's not a theory which is explaining. Probably because I didn't agree completely on the word theory. It's only that it's a theory, but you see, I adding formally the foliation as a parameter, and I can make a distribution of foliation in the theory in Bohmian mechanics without changing anything to the results. If I make an average on any observables, and I say that I can write. Normally, what you do in Bohmian mechanics is take this integral here. You suppose that is deterministic, so the observable will give you a value, and but the foliation is fixed normally. But now I can add a distribution of foliation on top of that, and it will not change anything because each of these terms is already giving you quantum mechanics. So if I have a ranging on that, and I suppose that I have a hidden variable for foliation, then it's okay. But you have to be prudent mathematically with the foliation distribution that you want to use. You cannot use anything because you are in space-time, so you have to be careful.
But Aurélien, so your statistical distribution, that's for the statistics, right? I think left meant something else. Left meant like using an average to define what's actually happening in a single universe.
Yes, it's true. It's not the same. Yeah. It's not exactly the same because in fact, he's considering in fact, there is one foliation at the end. So it's like you have a Dirac function distribution here. Because he wants to find a process which is defining the foliation in a univocal way. So, of course, tensor like the center of mass, for example, of a system could be a good way of thinking about it. And the CMB, the cosmological microwave background is also something related to that because you have isotropy and homogeneity. at the cosmological scale. So it defines also this kind of homogeneity, and this is fine. But in more complicated universe, it's not necessary to have this, and maybe actually, since everything is hidden, we have a lot of possibility there. And if you, yeah.
We still have time if you have one last comment on this. Otherwise, I move to the final question.
Very speculative everything. I agree that.
Ipo, you can go.
Yeah, sorry, it's going to be some clarification, maybe silly questions. It's about the Frauchiger-Renard paradox, because I know that you wrote about it.
Yes.
On the Bohm.
This one.
Yeah. And could you remind me? I don't know. So if you remember Renato assumptions, you had the universality, consistency, singular outcome.
Yes.
And so to you, what Bohmian mechanics give up, what assumption it is, and your new theory or your new take on Bohmian mechanics, does it change anything?
So this is okay. You know that the paper of Renato and Frauchiger was written in a very complicated way because he has a lot of questions, throwing them one after other. I did that in my manuscript, in my article here. But to go in I could not go to the detail of that now. But I can tell you that it's fitting quite well with the point of view of Rovelli about some bubbles of consistency. If you think about this erasing procedure here, from Dutch, coming from the idea that you have a quantum computer, and if you want to have interference between different framework of different observers, you need to remove this information. Otherwise, you need to erase this information. Otherwise, you have problems. And Rovelli was clearly telling that during the quantum knowledge limit of knowledge conference, that you can have different perspective from the point of view of different observer, but only if you don't, if you apply quantum mechanics correctly. So you don't need to, you are not allowed to introduce communication, mysterious communication between observers. Otherwise, you are breaking the coherence. You're introducing which path information, and all the deductions are simply getting false. And I think that one of the main problem was that in the paper of Renato is that he was considering that each observer is somehow keeping the information to the next stage, even though it is erased at the same time. So there is a lot of problem when you make the discussion correctly about that at that stage. If you see in Bohmian mechanics, there is no problem because I completely define the dynamic for all things together, and I consider carefully the coherence of the wave. Here I use there is no, if you use and also the foliation, but this is the point of the talk. But if you take an experiment like without with the two lab are not doing the same thing, you should see that experimentally because you have information which is shared with an environment. If you don't care, if you don't consider that possible, then you have problem. You know.
Okay, so Bohmian mechanics in this sense will still be universal, right?
Universal in that sense, yeah.
Yeah. Okay.
So
because it can be applied to any object, but you just have to be careful on how you describe your object. So
the paper of Renato was written with this effectively with these three postulates, this quantum rule, quantum mechanics, this common agreement, and that remember it was the self-consistency.
Yeah, it was a self-consistency assumption that was problematic in a sense because it was weirdly formalized.
But you see, sometimes to force people to answer to this framework, and then the framework is not sufficiently flexible, then if you want to go outside this framework, you are not allowed. So the problem is that he put the problem in such a way that you seem that you are not allowed to ask further questions. And are you believing that Q is correct, C is correct, or S is correct? And in my way of thinking, everything is true in the same time. You have no problem with quantum mechanics, you have no problem with consistency for one observer, and not problem with common agreement, but only if you apply quantum mechanics by keeping into account the coherence of the wave function at any time, and if you apply ontology at any time. Yes, otherwise you are blocked.
Okay. And so just a last clarification, I guess maybe you already said it a lot of times, but I don't know, it's just, I just want to be sure. In the voice theory, in the Bohm theory, what is, because since you can, yeah, what is the nature of the projection? I don't know if you still can call it a projection, but if you want to describe projection postulate in the Bohm theory, yes, what will it be? Will it be ontological? Will it be nomological?
Okay, the collapse. First, in Bohmian mechanics, in the Broglie-Bohm theory, there is no collapse per se. The wave function is always here. So it's also a source of question between the nomological versus let's say ontological schools. But you see in the Bohmian mechanics, the particles are following some canals, some grooves all the time. So if the wave is split in a Mach-Zehnder or in a Stern-Gerlach experiment, you have different waves, the particle is choosing one or the other, but you have never collapsing the wave. It's only that since you have particles which are trapped in some canals or others, at the end you can see only the canals which are active somehow. The other ones are empty. So it's also a source of discussion because David Dutch would say that is a kind of many words in Néel, including Néel.
Yeah, because I feel like depending on how you interpret that, it can be more or less close to maybe many words or Rovelli or stuff like this.
Yeah, it's true.
Yeah.
It's true.
Yeah. Okay. Thank you very much for the clarification.
Okay. Thank you, everyone. Let's thank Aurélien once again. Okay, so yeah, I'll see you all next week with Hippolyte's talk. Thank you for coming, everyone, and thanks again, Aurélien. Have a nice weekend, all of you.
Thank you.
Bye-bye.
Ciao.
Ciao.